Bienvenidos al Coloquio Nacional en Inteligencia Artificial. Welcome to the AI Colloquium. It's a pleasure and an honor for me to introduce Professor Andrew Davidson. He's Professor of Robotic Vision and Director of the Dyson Robotics Laboratory at Imperial College. His long-term research focuses on simultaneous localization and mapping, and its evolution towards general spatial AI, computer vision algorithms which enable robots and other artificial devices to map, localize within, and ultimately understand and interact with 3D spaces. With his research group and collaborators, he has consistently developed and demonstrated breakthrough systems, including the first mono SLAM system, Kinect Fusion, SLAM++, and Code SLAM. And recent prizes he has obtained include Base Paper at ECCB 2016 and Base Paper Honorable Mention and CVPR 2018. He has also strong involvement in taking this technology into the real applications, in particular through his work with Dyson on the design of the visual mapping system inside the Dyson 360 iRobot vacuum cleaner. And he's also co-founder of the applied SLAM startup SLAMcore. He was elected fellow of the Royal Academy of Engineering in 2017. And he's going to talk today. The title of his talk is From SLAM to Spatial AI. So welcome, Andrew, the floor is yours.
Thank you very much. Yes, thank you to everyone who's organized this talk for inviting me, and it's a pleasure to talk to researchers in Mexico. So I'm just going to share my screen. Good. Can I just check that that's coming through okay?
Yes.
Perfect. Okay, so thanks again. So yes, so as Enrique kindly said in the introduction, the title of my talk is From SLAM to Spatial AI, and I will explain what I mean by that. And in this talk, I'll show you some of the research that we've been doing over the last years that I've been working in this area, and also give you some of my general kind of thoughts about progress in this area, some very recent research, and maybe some thoughts about where things are going in the future. So we're at a kind of interesting point, I think, in this technology around visual SLAM. So visual SLAM is really the area that I've focused on through most of my career, and it's all about how do we enable a robot to understand the space around it and to estimate its position within that space. And in particular, I've been interested in doing that with vision, so using cameras as the main type of sensor. And I've been in this area as a researcher for, well, really since my PhD about 25 years ago when I started working on that. But now some of the technology that we started working on then has found its way into real products, and that's very exciting. I've just shown a few examples here, and actually they're in several different categories. So we have robot vacuum cleaners. So this is actually the Dyson 360i, which was a project I was personally involved in working with Dyson to design the SLAM system that's in this robot. There are mobile phones that now do visual SLAM. So this is an example of a smartphone that can estimate its position within a room and build a map of that room. There are visual SLAM systems within headsets for virtual and augmented reality. This is a demo from Microsoft HoloLens. And there's also visual SLAM inside various drones from companies like DJI and Skydio. So these systems, these are products you can buy. They actually have the capability to use cameras to map the space around them. And that's actually working well enough to be used in products. But I think it would be fair to say that all of these are fairly kind of early products in terms of the smart robotic products we might imagine in the longer term. So in terms of what they actually do with their visual SLAM systems, they do build a map of the space around them, but it's a fairly sparse and simple map of landmarks and points, for instance. They have some level of dense mapping and scene understanding, but they're fairly early products, I would say, in this area. So how can we understand the progress in SLAM? So it's taken quite a number of years just to get to that position where there are any products at all with visual SLAM. But one way I like to think about progress in SLAM is through levels of capability. So this is a slide actually from our startup SLAM core, where we think about levels of performance in SLAM, where level 1 is robust localization, essentially building a good enough map to know where you are in a space. Level 2 is dense mapping, which means actually trying to build a dense understanding of the scene around you, the shape of the geometry that's around you. And then level 3, which is very much a current research interest, is semantic understanding. So can you actually add meaning to the geometry that's around you? So a term I've been using recently is spatial AI. To really, for me, it's not something different from SLAM. It's something that SLAM has always been aiming towards and is gradually evolving into. So in my mind, this real-time vision mapping capability becomes useful when it actually enables a device such as a robot to be intelligent in the space that it's in. So SLAM is not just about positioning X, Y, Z. Ultimately, it should be about actually enabling a device to behave intelligently. And I think using this term spatial AI makes that more clear, that that's what we're aiming towards. So where might we get to in spatial AI in the longer term future? So there's a couple of ideas here. One would be a much more general purpose robot for the home. And this is just a kind of fake image that I found on the internet somewhere. It's not representative of any company's real idea for a product in this area. But imagine that you could buy a robot like this that would be a mass market, general purpose household robot for cleaning and tidying of complicated rooms and objects. So that would need to have a very, very capable spatial AI system. It would need to understand 3D scenes. It would need to understand objects. It would probably also need to understand people. But also, if you wanted to actually sell this as a product, its spatial AI system would have to fit within certain constraints of price, aesthetics, size, safety, power usage. So all of those things would have to be done within, constraints that actually might look like a consumer product. Here's another example product, which I think that if it existed would really change the world. So a really general purpose augmented reality system. So something that's not a heavy headset, but something that really has the size and weight of a normal pair of glasses. And it would have the ability to provide a robust and accurate real-time overlay and spatial memory of all the places and objects and people that you encountered in your life. So it would really be able to augment your intelligence in a very general way. So if that product existed, I think that could be the next, major computing platform that might maybe eventually replace the smartphones in our pockets. So products like that, either of those two that I've shown you, I think would be very impactful, but they don't exist yet. I don't think it's because there's no demand. I think it's because no one knows how to make them. It's too difficult. So exactly the kind of research I'm interested in is how might we get across this big gap from the current products that we already have. We have some idea of current research that's going on in my lab, in other labs, current prototypes, but I still think there's a big, big gap to this full spatial AI performance that might enable really general, powerful products like that. So especially when you consider the constraints of things like small size and low power. So it's no good to carry a room full of GPUs around with you, inside a small device, for instance. So some of my thinking about this area of spatial AI in general, I've recently been writing about in a series of papers. These are very sort of personal discussion kind of white papers in the future mapping series. If you're interested, you can find the first one and the second one on archive. If you go to my website, you'll easily find them. So really thinking about the properties of spatial AI, and there's a few hypotheses in there. In the first paper especially, there's some hypotheses that say that we think the properties of a spatial AI system are probably quite general. So that means even though there are many different possible applications, whether that's an AR system in glasses, whether it's a vacuum cleaning robot, whether it's a drone, whether it's something else, they will clearly have quite different needs, different performance, different constraints. But I think there's something common about how their spatial AI systems should work. And that's the sort of research that I'm interested in doing. So just another kind of recent piece of work that I'd like to mention, a project that I was involved in last year with this set of collaborators from a lot of different universities and companies, was also thinking ambitiously about kind of longer term goals, especially in robotics, and trying to specify a set of tasks that you might want robots to solve, which we gave the general name rearrangement. So if you've got something like an untidy room that you want to turn into a tidy room, or maybe you've got a set of parts that you want to assemble into some kind of object, we think there's a wide range of tasks that can be considered as some type of rearrangement. And the goal about thinking about things like this is to try and make some specifications of how you might judge the performance of an agent that's trying to solve a task like that. So whether it's in the simulation or whether it's actually a robot operating in the real world. Because I think, in my opinion, a lot of the work that's done in AI at the moment, and lots of the papers you read and challenges, they're not really ambitious enough. They're not really aiming for this very general sort of spatial understanding that would enable a robot to do anything like the kind of things a human can do. So that's another interesting paper to have a look at if you'd like to. And the final thing to mention in this kind of introduction is a particular project of ours from the Dyson Robotics Lab, which is actually mentioned in the rearrangement paper, is a project called RL Bench. So this is, I'll just show you a quick video. This is our own robot simulation environment, where we've implemented a very wide range of different robot tasks. So this is all based around a robot arm that's currently attached to a desk. But there's a whole load of challenge still just in this setting. But this is trying to give some sort of, again, ambition for the sort of tasks that we might want robots to be able to do in the future. So that's an open source project if people are interested in using that. Okay, so I'm going to come on to talking about some of our recent research in this area, but I'd just like to talk about a little bit of the history of the work in particular that I've done in SLAM and spatial AI. And in particular, this refers back to the picture I showed you earlier of layers of capability in SLAM. So for the first years of my career, from my PhD and onwards, I was particularly focused on localization. So in particular, how could we estimate the position of a camera which is moving through a scene? And in 2003, for the first time, we published this algorithm called MonoSLAM, which was the first time we were able to show real-time SLAM from a single camera. So I'll just show you this briefly. So here's the setup. We've got a single webcam, and it's just a cheap webcam. There's no other sensors involved, and it's connected to a computer. And we're moving this camera around inside a room in quite a general free 3D way here. And our goal is to estimate the position of this camera in real time, and to do that by building some kind of visual map of the scene. So in this image, you can see now the video from the camera as it's moving around. And you see that what we're basically doing is detecting and tracking a set of landmarks in this scene. So each of these boxes is a landmark feature point that we have automatically detected in the scene, which is a high texture point, which we think we can reliably track through the future. So you'll see that each of these is nicely tracked, and the colors indicate something about the quality of tracking. So especially the red points are the ones that are being, tracked repeatedly. We feed all of those measurements. So every time we find one of those features in an image, it basically gives us a measurement of the relative position of that landmark and the camera. We feed all of those measurements into a probabilistic localization engine. So here we were using an extended Kalman filter, which is a probabilistic estimator, which jointly estimates the motion of the camera and the position of the landmarks. So let me just pause this for a second. So this is essentially the output of our estimator. So this thing here that's flying around is the estimated position of the camera that's updated 30 times per second, once for every new video frame. These things here are the estimated positions of the landmarks. So each landmark has a unique texture patch that identifies it. But we're also displaying here these ellipsoid regions, and this indicates the uncertainty in the position of these landmarks. So you'll see that the more observations we get of the landmarks from different positions of the camera, we're able to gradually reduce the uncertainty and get more and more high quality estimates of where they are in the scene. So that's really the first level of SLAM. We're able to build a map that enables the camera to know where it is. But it's a very sparse map. So that map is not really yet giving us much information about what's in the scene around the camera. So the next level of capability is dense mapping. And we did various pieces of work on dense mapping going back to about 2010 with systems like DTAM and Connect Fusion. I'll show you this one. So this was from a few years later, a system called Elastic Fusion. So this is what we call a dense SLAM system. So we have a camera moving around through the scene. This is actually our lab room at Imperial College. And we are still doing SLAM. We're jointly estimating the motion of the camera and building a map of the scene. But now you'll see that the map of the scene is much more detailed than before. So rather than just a few points, we're now estimating the shape of the whole kind of surface of every object in the scene. So in fact, the representation of 3D that we're using here is a circle map. So if you look closely at this reconstruction, you'll see it's made up of millions of little tiny disks. But there are some nice properties of how this algorithm works. One is that it can do loop closure. So you'll see here that occasionally you'll see parts of the 3D reconstruction that don't line up, but we're actually able to detect those kind of misalignments and fix them. And in SLAM, that's what we call loop closure. So we're able to kind of correct these small errors that have built up. And there in just 2 or 3 minutes of scanning, we've been able to build this model of the whole room. So I should say that the camera we were using here is a little bit different from just a color camera. It's a depth camera, a bit like a Kinect sensor that also gives us depth information. But in fact, we are able to do this kind of thing also with standard color cameras. It's just it's harder and takes more computation and is hard to get as accurate as this. So that's dense SLAM, and then really the final kind of layer of capability to talk about now is semantic understanding. So the previous map that you saw, it's very, very detailed, but it's all still essentially just geometry, whereas a representation that's going to actually be useful for a robot to do intelligent things has to have something more. It has to have an understanding of what the actual objects are in that scene. So here you'll see where we're trying to color objects in the scene according to what type of object. So blue for chair, green for table, etc. So the first system that we worked on that tried to do semantic SLAM in a very general way in my lab was called Semantic Fusion. And this was the sort of result that we were able to get. And actually, this was quite a simple system in some ways, in that we were taking the previous system I showed you, Elastic Fusion. So we have an input stream of RGB and depth images. We feed them to Elastic Fusion and can do a 3D reconstruction. But then we also take those images and we feed them to a CNN. So this is a convolutional neural network that has been trained to look at images and label each pixel with the type of object that it thinks is present. So out of this CNN, we get a probability map for different classes. So this is the probability that every pixel of this image is part of the floor. This is the probability that it's part of the sofa. And then what we do is we literally just combine these two things. So we take the CNN probability maps from images and we project them into our 3D SLAM map. So then each little circle in our SLAM map is then holding an estimate of what type of object it thinks it is. And then we can actually get much better labeling of a scene by this kind of incremental 3D fusion than you could get just from labeling a single image. So these are the sort of labeled 3D reconstructions we were able to get. So if I look at this, I think, well, this is quite nice, but you can also see some of the problems here. So it's quite noisy looking. Sometimes there are mistakes, and also there's no sense of individual objects here. This is really just gray means wall, green means bed, but there's no sense here of whether there's one bed or two beds or anything like that. It's really just sort of painting semantic texture on top of the scene. Okay, so that was some semantic fusion. Now I'm just going to show you this diagram, and don't worry too much about the details of this. But the point I want to make is that this is representing something like the structure of the program that's implementing that semantic fusion system. And the main point that I want to make is this is quite complicated, and also it's quite kind of computationally costly. So there's a lot of data moving around between different modules here. So there's modules for tracking the camera, there's modules for labeling the images, there's modules for kind of fusing all of that together. There's modules for optimizing the map after a loop closure, for instance. And when we actually implement this on a computer at the moment, parts of this run on the CPU, parts of it run on the GPU. It's very, very kind of complicated. A lot of the data that's moving around this is also very large. So for instance, our map of the scene consists of 5 million circles. That's a huge amount of data. So we have this system, it runs in real time, but it doesn't work that well. It gives us something, but it's not the result we want. But also it has this very heavyweight and complicated computational requirements. So I look at this and I think, well, how are we going to get to this very high performance, very low power, very compact spatial AI that we might need for an embedded product? It seems like a very big gap. So I think a lot of our work is really trying to attack this question. And I think there are two kind of key lines of attack that we've particularly been interested in our lab. One is to think about representation. So can we get away from these kind of enormous data representations like 5 million circles for a room to something that is much more compact? Because that then would be maybe more meaningful, but also much more efficient. The other kind of line that I'm very interested in recently is how does the structure of the computation that you need to do here relate actually to the structure of the computational hardware, the computer processors that you're actually going to work with. So I'll talk about the first of these first, which is representation. And I should say something about SLAM and deep learning. So I've already shown you one example of how we're using deep learning within SLAM, the CNN that we were using to label the scenes in semantic fusion. And probably if you're working in any type of AI at the moment, you'll be having these kind of thoughts every day about, what's the right way to use deep learning in my application. I would say that in SLAM, actually it's maybe one of the areas of AI where deep learning has not yet, completely dominated how things work. A lot of really working SLAM systems are still mostly human designed. You look inside any of those products I showed you earlier, there might be some neural networks, but actually most of the important stuff is not neural networks. On the other hand, we are very open to deep learning and neural networks in SLAM, and in most of the research I'm doing now, we're using deep learning in various ways. I think there's very much a kind of sliding scale between systems that you might fully human design and systems that you might just try and solve with a single neural network. And what most people building practical systems are doing at the moment is somewhere in the middle. So something quite modular, parts of it that you do know how to build and design, you build them like that, and you won't be able to beat that with deep learning. Parts that you don't quite know how to design, like for instance, semantic labeling is something that we just never knew how to do that without learning. Learning made it much better. But something like geometrical estimation and tracking a set of points and estimating the motion of a camera, there's still no better way to do that than the human designed algorithm. So we're building these kind of modular algorithms, but very much where learning can be useful, I think, is in this question of representation that I mentioned. So when you've got something like a huge map of circles, what learning can do is try and find a kind of embedding a much kind of smaller set of numbers that represent the interesting variation in that scene. So actually, you probably don't need 5 million parameters to represent the things that are interesting to a robot about a room. You can learn something much better. So a lot of the work that we've been doing is along those lines. So a couple of projects to mention from recent work are Code Slam and Scene Code. So these were projects about essentially trying to do that. So don't worry too much about the complicated picture here, but we're trying to find from a data set the relatively simple sort of variation in scenes. So if you have so we actually used a simulated data set here. So we've got a simulated kind of computer graphics rendering of indoor scenes. And if you take a depth map from one of those indoor scenes, it will have a lot of variation. But if you look at millions of those depth maps, you can actually learn that the sort of variation that you see in natural scenes is much lower than all of the pixels in an image. So for instance, natural indoor scenes tend to consist of continuous solid objects, and therefore the depth of nearby pixels is much more likely to be very similar. So the world is not a random point cloud. The world has a lot of structure, and we're learning about that in these systems. And maybe if I just show you this video here. So this is Scene Code, where we're using this approach to have this kind of coded, learned representation, both of the depth structure of a scene and of the semantic content of a scene. So if we contrast this video with the Semantic Fusion video I showed you before, in a way they're trying to solve a similar task of taking multiple images and trying to fuse them into a 3D representation and estimate the semantic labels of that scene. But you'll see that the sort of performance is quite different. So in some ways this looks more kind of low resolution, it's kind of a bit blobby, but on the other hand it's much more coherent. It doesn't have this kind of speckly noise. So we're not, you can see sometimes we get things wrong and we're not sure whether this is, for instance, a bed or a sofa. But it's not like we think this pixel is a bed and this pixel is a sofa and this one is a bed. Either we think the whole thing is a sofa or we think the whole thing is a bed. And when we get a bit more evidence, we're able to kind of flip the whole thing over. And that seems to be a much kind of smarter thing to do. So have a look at those projects if you're interested in. And in fact, that we have a project called Deep Factors, which is a kind of evolution and a fully probabilistic implementation of these code type of methods, which is available as an open source project. So have a look at that if you're interested in that work. You can download that code. So another project that I will show you, which is in the same sort of area of trying to use neural networks to represent the 3D shape of scenes, is actually a very new project that we've only recently put online, but it's one that we're quite excited about, called IMAP. So this is quite closely related to things like NERF, if you may have heard about that, which is a quite famous paper, which is using a general purpose multi-layer perceptron, so the most general type of neural network, to represent the 3D shape of a scene. So this is really a neural network where you feed in a coordinate and the network learns to output for every coordinate that you feed in what is the occupancy of that point in the scene. So it outputs 1 if it thinks that's part of an obstacle and 0 if it thinks that it's part of empty space. So what we have done in our new work called IMAP is to implement a real-time SLAM system for the first time that uses this type of implicit neural network-based representation. So here's the system being demoed by a PhD student, Edgar Sukar. So we move a depth camera around this scene in real time. And then here, what you can see is real-time optimization of this implicit neural network, which is representing the scene. So as we capture every new color and depth image, we're using that as a sort of extra piece of training data to help us improve this neural network. So you can see, you know, the actual data captured from the camera at the top here, and then just below that, these are the renderings from our neural network. So if the neural network's working really well, then these renderings should look the same as the actual captured data. And you can immediately see that this has some really nice properties, this network. So it gives us a really sort of smooth and continuous representation of the scene. And one of the sort of really cool things it's able to do is to fill in areas even where it wasn't able to observe them. So there are some objects over here kind of on the right-hand side of the room. We've never seen the back of these objects, but the neural network, it has to generate an occupancy value everywhere. And it does a pretty nice job of kind of filling in plausible values for the back of these objects, even if we've never seen them. So this is very, very, very new work. So another very nice property of this is that this is actually quite a small neural network. So it only has about 1 megabyte of weights, which means it's really a very kind of compact representation of the geometry in this room. And that's one of the reasons we can actually run a system like this in real time. So we're actually training in real time to represent the shape of the scene. I'll just show you this part where we show that this is a genuine 3D representation, and it's very kind of, you know, smooth and complete. Okay, so that system has this property of learning this kind of quite efficient representation of a scene using general purpose learning mechanism. So another kind of big focus of how do we use learning together with SLAM is to focus much more on the objects in the scene. So yes, we can represent the whole shape of a scene, but actually if a robot wants to do intelligent things in a scene, it doesn't necessarily need to understand everything. What's really important are the objects that it could possibly interact with. So we've got a series of very promising work on really building SLAM maps that focus on the objects that they contain. So the first piece of work we did in this direction, and it was a bit of a kind of landmark project for us, was called SLAM++. So this was now a few years ago. If I just quickly show you this video. So this was a system where, you know, similar to Elastic Fusion, it's a real-time depth camera system. So we're moving a depth camera around in this scene. But different from Elastic Fusion, we're assuming here that we have prior knowledge of some of the objects that are going to be present in this scene. So here we've got, for instance, some chairs and tables. And actually, these are quite specific chairs and tables. So we know that this exact type of chair and this exact type of table are present in this scene. So then as the system progresses, we don't just do bottom-up mapping of the scene. We're immediately doing object detection, and we're trying to detect from the input depth images of this camera whether there are any instances of these known objects present. So you can see in the scene there's many chairs here, and then you'll see them appear in the SLAM map. So that the map only exists at the level of objects. There's no sort of incremental reconstruction. You'll see when we detect a chair, the whole chair is kind of popped into the map. And then the chairs take part in this factor graph. So they kind of become landmarks in our SLAM system, a bit like the original points in MonoSLAM. But now each one of those landmarks is a whole object. So that was very promising. But the obvious limitation of this system was that, this worked for these very precise objects. So it only worked for, this type of chair and this type of table. So one of the things we've really been interested in generally is, first of all, how far can you go with that, with assuming that you do have specific knowledge of objects, but on the other hand, how can you relax that assumption? Excuse my telephone in the background. So first of all, if you do have not knowledge of the shape of objects in the scene, what can you do with that? And actually, that's not a bad assumption in many robotics situations, I think, because imagine the robot of the future. It's probably connected to the internet. It probably has access to huge databases. There's actually no reason why it might not have, an awful lot of, knowledge about objects that it would typically find in a household, for instance. So in this system, we assume that our robot has precise knowledge of the shape of the objects it's going to encounter in the form of CAD models of these objects. It's going to fit them and try and estimate the position of these objects, but in a more difficult situation than we had in SLAM++, because these objects are actually, they're in clutter, they're on top of each other, they're occluding each other. So here we show that we can build a system. So here now it is a SLAM system, but we have a camera that's mounted on this robot arm. So the robot arm moves and observes the scene. So you'll see that as the camera's moving around, we get these different color and depth views. We do some volumetric reconstruction, and when we've got enough confidence to estimate the position of one of these known 3D objects, we replace the volumetric reconstruction with actually the CAD model pose estimate for that object. So eventually this reconstruction will become, quite accurate in terms of estimated poses of all of these objects. And we know that, real objects can't intersect each other, real objects must lie on top of each other and that kind of thing. So those things help us to estimate the position even of the objects that we can't fully see because they're underneath other objects. And then I'll just show you here something we can do with that, which is a robot task. So here's a situation where the robot comes across this cluttered pile of objects. Actually, the one it's interested in is this red box, and it would like to move it over to this brown area here. But it can't immediately do that because when it reconstructs the scene, it figures out that there are some other objects on top of that. So once it's got enough confidence about that, it can start doing some grasping. So it's got a suction gripper here, and it first of all has to pick up these objects that are in the way. It moves those off to this bin over here. And then once it's cleared those away, then finally it can grasp this red box and place it over here. And a thing to note is this is not just dropping it into the box, because it's picked this up this known object in a known way. It can actually place it very carefully into a known position in the box. So that was with fully known objects. So what can we do if we don't have full knowledge of the objects in the scene? In the weakest kind of situation, we might only be able to segment objects, but we don't really know anything about what they are. So in this system, we build a SLAM system which builds a map of objects, but it individually builds a reconstruction for each one. So here we're using a neural network, masked Gaussian, which can give us segmentations of objects in the scene, but we don't have any particular prior knowledge about the shape of these objects. So all that we do is for each new individual object, we have a separate 3D reconstruction. So the overall structure of this map is a graph of objects, but each object is individually reconstructed. So that's nice because we can deal with pretty much any type of object, and you'll see all these different objects that are being put into the map. But the disadvantage is that we can only really reconstruct the parts of the objects we can see. So some of these objects, you'll see the reconstructions, they have holes in them, and we haven't reconstructed the back of the objects that we've never seen. So to tackle that, some of our latest work is kind of somewhere in the middle. So what if we have partial knowledge of the shape of objects? So in this system, we have kind of class graph-based neural object descriptors. So here we specifically look at 4 types of objects. So we've got bowls, cups, bottles, and cans. And for each of those types of objects, we don't have a specific CAD model, but we do have general knowledge of the type of shape of those objects. And that has come from a large database of CAD objects. So for instance, we've got 3D models of 500 different types of mugs. From those mugs, we use a neural network. We actually use a 3D variational autoencoder to learn a low-dimensional embedding of the type of variation that you get in the shape of mugs. And then what we do at runtime, having detected that this is a mug, we then optimize the code of that learned model to fit the observation that we're getting. So you'll see that when we add new objects into this 3D map here, we have this optimization phase where the objects appear, but then their shapes are gradually adjusted until they fit the shape of the observations that we're getting. And then again, we're basically building a map out of these objects. So we kind of use each one of these coded objects as a landmark. And here's a kind of larger example where we're going to take a camera all the way around this table and gradually add to and build this map of the 3D objects in the scene. So let me just skip forward again here to an example of using this sort of system for robot manipulation. So here's a robot looking at a scene where there are several cups and bowls. It observes the scene from a couple of viewpoints and estimates the shapes and the positions of the objects in the scene. And then once it's got enough knowledge, it then goes into a grasping phase where first of all it picks up the bowls, and its goal is to place the bowls into this box and actually stack them. So it picks them up in order of size. It picks up the biggest one first. It carefully places it in here. Then it picks up the next biggest one and drops it to stack inside, and then picks up the next one and stacks it there. And then it, okay, there's the last bowl. And then it picks up the cups and places those also neatly into the box. So you see a lot of work on robot grasping where people kind of stop at the grasp. So that you grasp an object and then you just have to drop it. But we're very interested in, really precise grasping of objects such that you can precisely place them and do things like this, like tidying up, because that is much more useful, especially in the applications I'm interested in, mainly of indoor robotics. And I would argue strongly that doing this kind of precise manipulation and placing really strongly motivates having a full 3D understanding of the shape of things. Okay, so we're coming to the end. I'm just going to talk rather quickly about the last section here. So when I showed you this picture earlier, I said that I thought there were 2 kind of key angles of attack to try and tackle this very complicated, expensive sort of computation graph that we have in Semantic Fusion. And the second one of those is hardware. So a long-term interest of mine is thinking jointly about algorithms and the hardware that they will actually run on. And when I say hardware, I mainly mean processor hardware. I'm also somewhat interested in camera and sensor hardware, because I think we've been doing robotics and vision and AI for a long time using hardware that wasn't really designed for this. So we use cameras that were built for photography. We use computer processors that we used, that were designed for graphics, for instance, like GPUs. Yes, they can do some things in AI pretty well, but I think they're nothing like the end game of, if we could really design hardware for AI, for robotics and vision, we'd probably end up in different places. And if you think about the algorithms you want to run, then you can think about what sort of hardware is best. And also maybe eventually you can influence the design of hardware so that people might build hardware that's much better for the things that we want to do. So just to firstly briefly mention in the sensor area, one thing we've been very interested in for a few years was event cameras. So you may have heard of of these. So whereas normal cameras capture whole frames of intensity, an event camera has a pixel by pixel asynchronous measurement of change of intensity. And out of an event camera, you get a low bit rate signal just about what has changed in an image. And that immediately appealed to me as fitting in with this idea of, being much more efficient. And we did a lot of work on trying to actually build SLAM systems that used event cameras, and this is one of the visualizations of that. I don't have time to go into that much more. So what I'll talk about a little more is work around processors. So, SLAM algorithms run on computer processors. Eventually, we would like them to run on tiny, very efficient processors. So I was involved in one research project in particular called the Pamela project, which was a joint project with several universities in the UK, really looking at the performance of different SLAM algorithms on different processing hardware, from a huge GPU down to a tiny embedded board, trying to figure out what were the things that worked well, what were the things that didn't work well, and trying to open up some of these questions about what sort of hardware would be really good for this, but also still efficient. And there are really interesting things going on in computer architecture at the moment. And in particular, there's a new type of processor called a graph processor, which I find very interesting. So in fact, there's a company here in the UK called GraphCore, which designs a processor called an IPU, an intelligence processing unit, which they argue is much more suited to AI workloads than a CPU or a GPU. So an IPU is a massively parallel processor. In that sense, it's a bit like a GPU. It has many, many processing cores on one chip, like 1,000 or more. But the way that these cores are arranged and the sort of work they can do is very different from a GPU. So GPU is good at workloads where every core is doing the same thing all of the time, whereas an IPU is much more general. Each of these cores can be doing different work at different times, and then it has a very powerful interconnect structure. So you can have message passing going on between these cores with quite arbitrary patterns. So you call it a graph processor because this is good at implementing workloads that are well specified by a graph structure of different nodes that are connected together. And for me, that's exciting because a lot of the problems and algorithms I'm thinking about in SLAM and Spatial AI, they're all about graphs and how things connect together. So I've got very interested in thinking about how we can find the graphs in our SLAM algorithms and then map those down onto very efficient computing hardware. So this is one of GraphCore's visualizations. So they have a graph compiler that can take an algorithm or a neural network and compile it down, find its graph structure, and map that onto hardware. That's just a really nice visualization they've come up with. Something that I've thought about a lot and is particularly discussed in the future mapping papers is finding the graphs in SLAM algorithms and how we would therefore then lay them out on really efficient computing hardware. And there's several really obvious graphs in SLAM, such as the kind of connectivity of the different places in a map is usually well represented by a graph that looks something like this. So this is very much ongoing work. Now we're very much on to thinking about what could be the actual algorithms that could implement this type of graph processing that could be really good and efficient for SLAM. And in the second future mapping paper, we discuss that in more detail, and in particular talk about Gaussian belief propagation as a general sort of algorithm which we think has the right properties for. It's something you can implement on a graph using message passing, but it's able to estimate jointly consistent things across a whole distributed architecture. And actually, this is not a new algorithm. This is an algorithm that's been known about for several decades, but it's an algorithm that was a bit sort of put to the side, maybe because it didn't work very well on the sort of computing hardware that's been around. But I think it's a strong candidate for the sort of algorithm that may come back strongly with this new type of graph hardware. So the most kind of concrete piece of work we've done so far is a paper we had at CVPR last year called Bundle Adjustment on a Graph Processor, which uses Gaussian belief propagation to implement the well-known computer vision challenge of bundle adjustment, which is basically jointly estimating the positions of a set of cameras and a set of points, but using a very different sort of algorithm from what's normally used on a CPU, and showing just that we can run very, very fast using this distributed belief propagation algorithm on an IPU and really get breakthrough performance. So we think that's a great kind of marker for some of the directions we might go in the future. Okay, so I'm going to conclude now. So so just some final thoughts. So spatial AI research is what I'm going to keep working on for the foreseeable future. It's very exciting. I think that some interesting research areas for me are efficient 3D scene representations and systems for incremental scene understanding, co-design of processors, sensors, and algorithms, and integrated graph-based algorithms for estimation and machine learning. So just to mention my affiliations, so I lead the Dyson Robotics Lab at Imperial College. So this is an academic lab which is funded by and collaborating with Dyson, a company in the UK that has great ambitions and ongoing research in home robotics. And our lab, has openings for postdocs and PhD students. We do long-term research on SLAM scene understanding and manipulation. And then my other affiliation is with SlamCore, as I mentioned earlier. This is a London-based startup company, and we are working on applied spatial AI solutions. So that's it. Thank you very much. And I will stop sharing my screen and see if anyone's got any questions.
Thank you, Andrew, for a very interesting talk. So there are some questions already coming from the chat. I'll read the questions for you. So one is, the first question is, say thank you for the nice talk. In most deep learning-based semantic segmentation systems, only typically gets map values for the semantic classes, and in some sense, we lose the ability to handle uncertainty at this semantic level. Are there easy ways to integrate the source of uncertainties too?
Mm-hmm. Nice question. It is definitely a tricky thing. We've looked at various aspects here. So in the original Semantic Fusion system, so actually we do use uncertainty to some extent there. So from each individual frame of semantic labels, we have a distribution over classes. So we get these kind of final one-hot vectors from our network indicating that what the network thinks is the probability of each class for each pixel. And we do actually fuse those in a Bayesian way. So each of our circles is holding a distribution over classes, and then every new measurement will kind of be fused into that distribution. So it does happen to some extent that the more the more confident measurements that you fuse, the more and more confident the probability of that circle's label becomes. On the other hand, I think the big thing that's not taken account of in semantic fusion is every circle, every little point in the scene has an independent distribution over those probabilities, and that's clearly not the right thing to do. So in some of the more recent work, like Code Slam, scene code, and so on, so especially scene code here, we are, it's this small code that generates a semantic label map for the whole image, but the way we estimate the right scene code is done in a Bayesian way. So there we do get the ability to kind of combine information from multiple sources into the estimation of this one code. And the code, it controls whole areas of the scene in a more sort of continuous way. So then, when you got some extra information, as you saw in the video, for instance, a whole area of the scene might suddenly flip to a different category where the probability gets higher. But these are definitely still ongoing difficult things that we'll keep working on. And in general, the interaction between kind of proper Bayesian probability and neural networks and how to do that properly, I think is still a very tricky thing.
Okay, I have another question from Raul Rojas. So he says, when you match a scan of 3D data points to a library of CAD objects, how do you select the subset of points that you match to a chair or a table? Mm-hmm. Are you running the align algorithm against the full set of objects in the library?
Yeah, and another good question. So at the moment in the demos I showed you, yes, and that's because the library of objects is fairly small. So certainly in SLAM++, we were only using, I think, probably in the demo I showed there's actually only 4 classes of objects that were actually active in that demo, and there was some kind of exhaustive search through those classes. So clearly that's not very scalable. But I think the path to making those things more scalable is quite well understood in object retrieval, in image retrieval. So there are many well-known ways to do image and object retrieval over much larger databases using some of the methods that go back to like text retrieval, bag of words, those kind of methods where you build a kind of inverted index and this kind of thing. So yeah, so in the demos you saw, we were doing something pretty simple, but I think there are quite well understood ways to try and scale to much larger libraries of objects.
Okay, there's another question. Hi, thanks for the talk. Have you investigated what kind of structures are formed inside the implicit maps?
Well, something we're very much doing at the moment. And that's interesting because it's not immediately obvious how to do that. So yeah, exactly what you'd like to find out is, which of the weights in the network are generating which parts of the scene. So that seems like a very interesting question because it tells you how the network is compressing the scene. I think some aspects of that are quite obvious just from kind of looking at the system. So one of the things I often point out is, so in the IMAP video, there's like a football on the floor, and it like an orange ball, and you can see it kind of oscillates a bit. And interestingly, so our whole map kind of oscillates a little bit, and that's just because there's stochastic training going on all the time in the neural network. But the fact that the whole shape of the ball kind of oscillates in a very coherent way, so in fact the whole ball gets a bit bigger and a bit smaller, really shows me that there aren't many weights in the network that are generating the shape of that ball. So if there were 1,000 weights in the network that were generating the shape of that ball, it would be very unlikely that they would all change at the same time such that the whole ball would get bigger. But if it's only 1 or 2 or 3 weights, that's not that unlikely that they would all change at the same time. So that sort of type of analysis of perturbation and or to be honest, that's leading us towards something we're very interested at the moment, towards kind of tagging and labeling these scenes. So if you see how one part of when you change one part of the scene, which other parts of the scene also change, that kind of tells you which parts of the scene are generated by similar paths through the neural network, and that's very interesting. But again, another question where I think we still have a lot of open questions. So another kind of recent thing we're thinking about would be, in IMAP we are optimizing that network from 0 every time we're in a new room. Sometimes that's a really interesting thing to do, but it seems like it would be useful to carry over some prior information. where would be the right place in the network to sort of maybe lock to represent this as prior information? That's something I don't think we have good answers to yet.
Well, I have a question. So I'm quite interested in this idea of belief propagation, in my background in graphical models. So my question is, how do you integrate this idea with the deep neural networks, these implicit representations? How can you combine?
Yeah, funnily enough, I was talking to Edgar about this about an hour ago. Yeah, I've got some ideas. Actually, my main ideas are about keeping the factor graph and Gaussian belief propagation as the kind of the master structure, but within that, putting in kind of modules that behave in a more general learning sense. So rather than designing the whole factor graph, having some kind of learnable blocks within there that operate a little bit like neural networks, but are actually updated using the rules of belief propagation. That's my idea at the moment that we're starting to try and work on. Because I think that would have so many advantages if you can really make your learning system and then your more general sort of representation and geometric system, if they work within a unified form and they're using probabilistic principles, then I think certain things might work much better and might give us actually finally answers to how to properly deal with the uncertainty that we get out of neural networks. But yeah, we're going to need a bit longer to figure that one out, I think.
Okay. Well, probably I think that the last question, what kind of interesting applications do you foresee in the future using spatial AI systems?
Yeah, I mean, I feel like there's almost no limit. So I feel like this, there's this future vision of spatial computing, if you like, as the sort of next great computing platform. So imagine you really did have tiny, efficient devices, with cameras and other sensors that actually understood the space around them. And maybe they can also communicate with other devices and build a sort of global understanding. I think that there's no end to the things that you could do with that. Of course, there's probably many challenges and concerns as well, because it seems like very powerful technology, I think. Yeah, so some of those devices might be robots. They might be sensor arrays that could be monitoring things. They could be cleaning. They could be I don't know, going around and cleaning up waste or something in the world and solving problems that are very hard to solve at the moment. I think the kind of augmented reality application in particular, when people really get that to work, I think that's going to be revolutionary because at the moment, everyone's got used to carrying a computer with them all the time, but it's in your pocket, your smartphone, and you have to keep kind of bringing it out to look at it. If that computer, was really sitting in here and it was able to display information to you on top of the real world, that would give you a sort of superhuman capability. You would never forget anything. Again, many challenges and difficulties that would present, but I do think that there's no limit to the sort of thing that you could do with this technology in the longer term.
Okay, well, thanks, Andrew. Thanks very much, and I think we'll now terminate our Coloquio today. Thank you, everybody, for listening.
Thanks very much.